So today, I'm going to move on to regression. So one announcement about the final project. So the final project has two parts. The first part, the last part is the final project. And well, let me finish for these guys to finish. All right, so the first part is to tell us your idea of what you want to do. And give us a little summary of your plans, where you're going to get your data and all that. Then the final project, that's not a big part of the grade as compared to the final project, which is to actually do the analysis and make a presentation. So so that's coming up. We'll announce it when it's due. It might be part of homework 3 to do that. And then in the final, you don't have to be here for the presentations. We're going to pick the best ones, and they're going to present. But I'm getting a lot of questions about can I go back home? And I don't know who in their right mind would leave and miss out on these great presentations. But if you want to leave, it's optional to be here for the final. Okay? Any other? Well, yeah, the project you have to finish it, sure. Okay. So anything else you wanted me to say? You guys wanted me to say? Okay, well, let's go. Then let's get started. Oh, the pointer is not here. Okay, so I'll go and. All right, so today we're going to talk about Moneyball, and we're going to talk about how data is used to pick baseball players for baseball teams. And we're going to see data, and part of the homework is going to be to do it yourself. So just to give you an idea of what's coming in the homework, we're going to ask you to build a team. You're going to get some amount of money, some limited amount of money, like Billy Bean had in 2002. And you're going to have to you're going to have to buy players with that money, create a team, and then we'll see how many runs that team would have scored. That's the idea of what we're going to shoot for in the homework. That's the general idea. So today we're going to talk about how you can use statistics to do this. Because there's not everybody knows the rules and the statistics in baseball, I'm going to go over them briefly. I'm going to go over only what matters for the homework and a little bit more maybe just to make it a little bit more entertaining. But it's not going to be much. You don't have to know that much about baseball. You don't have to learn the 100 and some rules that baseball has compared to the 11 rules that soccer has. I don't know how many soccer has, but it's not many. It's like you can't touch the ball with your hands. What else? It has to go into the hole, into the goal. All right, and there's this offside. That's it. In baseball, if you throw your glove at the ball, it's a triple. But the ball is live. That's one of the rules. You can walk up the foul pole and catch it. That's permitted. All this are in the rule books. All right, so let's talk a little bit about what you need to know for this homework. All right, so very next. Are you going to learn about baseball today? So the goal in baseball is for you're going to go up to the home plate, stand there, and try to hit the ball that a pitcher throws. So the pitcher is the guy who throws the ball, and you're going to hit it. And you have to hit it inside those lines. And then there's a series of people, little numbers there, 1, 2, 3. You can see 1, 2, 3. Those are the fielders, and they try to catch the ball in the air or tag you before you get to one of the bases. So you want to get to one of those bases and eventually come around. And when you come around, that's what counts. That's a run. When you get all the way around. So, runs is going to be the outcome of interest for most of the things we do. Ultimately, it's a win. We want to win. That's all that matters. But it's a little bit hard to do defense, so we're going to focus on offense. So we're going to try to predict runs. The team that scores the most runs wins the game. All right, it's not a point. Don't say a point because it make me very angry and I'll take a point off. Okay, so I'm just kidding. You can say point. So that's the idea. Okay, so what are the things that can happen? So why is this? very statistical in a way. So when you go up to bat, pitcher throws a ball, and a series of things can happen. One of them is that you strike out. You're an out, and you're done, and you go and sit down. So the team has 3 outs 9 times. So you get 3 outs 9 times to get as many runs as you can. So if you strike out, you're out, you sit down, you failed. That's a 0. If you hit the ball and you get to first base without the other team catching it, then it's as a success. That would be a 1. That's one way to start codifying all this. So you have success and failure. There's another way you can not fail, and it's if the pitcher doesn't offer you something to hit, and he has 4 chances, and if he doesn't, then you get to go to first base, and it's just like getting a hit. Okay, so that's called a base on balls. We're gonna use that today. Another thing that happens is when you hit the ball, you can go past first. You can go to second. That's better because you get closer. That's the second little white diamond. You can go to third. That's called a triple. Or you can go all the way home. If you hit the ball outside of the park, that's a home run, and you get to run all the way home and get 1 run. But you want to get as close as possible. So a home run is the best thing you can do. A triple is the second best. A double is the third best, and a hit is the 4th best. An out is just failure. That's what you want to avoid at all costs. There's other technicalities. For those that know the game, I'm not going to talk about errors or hit by a pitch or any of that, but it doesn't really matter much in the grand scheme of things. Okay, now, what we want to do is we want to pick players that are the most successful at getting runs. And there's some obvious things, like if you hit a lot of home runs, then of course you produce a lot of runs. There's another somewhat obvious thing, and is if you are very rarely out, then that's also a good thing because you're not failing. So those are the kinds of things we're looking for. Now everybody's looking for this, so there's going to be certain of these types of successes that are so obvious and people know about them, and they're going to pay for them. So what we're doing is trying to find out hidden things, hidden types of successes that will cost less. Right? Because we're a poor team, you have to now put yourself in the mind of the homework. We're going to have not a lot of money, and we have to spend it wisely. So players that hit a lot of home runs get paid. You need to pay a lot for them. Players who get a lot of hits. So the hit, again, I'm going to get to that now. So when you hear about baseball or go to baseball park or read it on the newspaper, they're talking about statistics all the time. And they're summarizing what the player has done up to now. And there's 3 really well-known statistics that you see all the time. So if you go to a baseball game, and this is starting to be less true, but it used to be just this. And you go, just what I'm about to say. There's a jumbotron, and when the batter's up, they put up all their statistics. This is an example. That face is actually like 50 feet big if you go to an actual game. So you can see there's something up there that says AVG. That's the average. We'll say what that means in a second. And then there's 2 at the end, HR and RBI. The games, that doesn't matter, just tell you how many games he's played. And if you notice, A, B, and H are redundant because if you divide 40 by 100 divided by 143, you see what you get? What do you get if you divide 40 by 143? The average. So see, 40 divided by 143, that's the average. So what they're doing is they're saying, every time I go up, if I hit the ball and I get to first base, I get an H. So this guy, Yunel, has done this 40 times at the moment this was put up, and he had tried 143 times. So you get an average. That's like in the polls, the percentage of ones. That's the same thing. So this is going to be like a binomial as well, assuming there's luck involved. Okay, now one little subtlety that actually matters. The at-bats, the AB, is not exactly the number of times you tried. There's something else that's nowhere up there. Well, it is up there in one place. Called the base on balls that is not given any kind of special attention. If you go up to bat and you get a base on balls, that means the pitcher never let you, they didn't give you an opportunity to hit, so you go to first, just like if you had gotten a hit. That doesn't count for the ABs nor the H's. It's like not there. It's a statistic that's not even shown. Now, what is the difference between a hit and a base on balls? There's some slight differences in terms of who can score on both situations, but they're pretty similar if you think about it. You don't make an out, that's the most important thing. And you also get to first, which gives you an opportunity to later come in. Okay, so those three, average, home runs, and RBIs. When I was a kid, when you watched the TV game, when you watched the game on TV, the batter would come up, and those were the three things that would show up. So that was like, that defined the player. So anybody know why they use those? Why are those? Why do we show the average? In a way, it's saying how good they are, right? That's what they're trying to get to. But what is it? How does it relate to runs? We don't know. We can look at data and see. But there could be other things we could report. But that's what's reported, and that comes from some person in the 19th century, I think, decided on this, and then stayed. That's just what we do. They just decided on that. They thought that was good, and we've stuck with it. Home runs, also same thing. It's a home run. It's good. You get home. You can run around the bases and score a run, so that's good. And RBIs, we're not even going to talk about that. But all I'm going to say is that the RBI depends on not just you, but other people. Somebody else has to be on base for you to get an RBI. So that statistic is not really a personal statistic. It depends on others. Average and home runs are pretty much just you. So it's your failure or your success. Okay, any questions up to here for those people who are just learning about baseball? No? All right, so here are some of the terms you need for the homework. Oh, no, before I go to that, sorry. I just have to show Bill James, who realized a long time ago, this guy was working in some odd job. It was like a security guard. He was a security guard in some company, and he spent his time looking through baseball statistics and thinking about baseball statistics. And he would write a little document. He would write up on his ideas on baseball just based on the statistics he saw. And he wrote this little book, and he called it the Abstract, Baseball Abstract, I think it was called, something like that. And he started just putting it out there, and it became so popular that everybody just started buying it, and it became almost kind of his new job. Now he's hired by the Red Sox to consult. But he was the first one to start thinking about summarizing players in a way that predicted something useful, like runs or some other thing that related to wins. So he's had a lot of ideas related to that, where he uses data and thinking of mathematics to summarize how good a player is. So now there's a bunch of other people that do what he does, but he was the first, and he was on The Simpsons. There's a little picture of him from The Simpsons. And now I guess he lives in Boston probably. Okay, so here are some of the terms that we're going to use. There's a lot more than this. When you get your database, it has a bunch of stuff. But this is what we're going to need most. Okay, or need for the homework. All right, and actually we might not need all of it, but this is a small subset. So runs, that's what counts. Whoever scores the most runs wins. At bats is the number of times you have an opportunity, but not counting base on balls. So if you add at bats and base on balls, that is very close. There's some little exceptions, but it's very close to the number of times that you go up and try. Those are called plate appearances. It has another name. So there's plate appearances and there's at bats. At bats plus base on balls is almost, we're going to assume, is the same as plate appearances. Okay? So strikeouts, how many times you make an out, it's a special kind of out. It's the worst kind of out where you don't put the ball in play. If you strike out a lot, it usually means you're not a great player. A hit is when you hit the ball and you get to one of the bases. But there's 4 kinds of hits. There's singles, which means you only got the first. Doubles means you got the second. Triple, you got the third. Home run, you got the home. So we have a third. We're going to want to create another one that is 1B, because 1B is not there. 1B is when you just get to first. So H divided by AB gives you average. So that doesn't matter which kind it is. And then BB is base on balls. So some observations right before we get started. When you look at let's say you have a player who hits a lot of home runs, a lot of doubles. Like David Ortiz, Big Papi from the Boston Red Sox does that. He hits a lot of home runs and a lot of doubles. And then you have another player that hits a lot of singles. Derek Jeter is an example. Ichiro Suzuki is another. Which of those two, if their number of hits is the same, which one do you prefer? Assume they have the same number of hits. One hits a lot of home runs and doubles. The other one hits a lot of singles. So you have to know how to answer that to keep up with the class today. So what is it? Which one do you prefer? Home runs and doubles, right? It's the same. A hit gets you to first. A single gets you to first. A home run gets you a run. A double gets you to second, which is closer to home. Okay, so doubles, singles, doubles and home runs get you, and same for triples. But triples are very rare. We're going to see they're not very informative. Triples even better, but it's very rare. Okay. Now, how about someone? If you have a player that hits very few hits, but has a ton of base on balls, and then you have another one that gets a few hits, so it has a higher average. Now we're going to have to start thinking which one of those two do we prefer. And that's one of the first insights that Bill James had. It's kind of obvious today, but he was the first person that started talking about, why don't we ever look at base on balls? It matters. And we're going to see that one of the biggest insights that Billy Beane had, and thanks to Bill James in a way, was that he looked for players that had a lot of base on balls. We're going to see that today. Okay, any questions? Okay, so let's see what the data says. All right, so when you do your homework, you're going to get these tables. There's 2 tables we're going to use, 3 tables we're going to use. There's a team table, which is this one. There's a player batting table that goes year, player, and it gives you these same things. And then there's a salary, which you need to get to know how much to spend. So this one is a team. This one summarizes everything. So we have the team, and then you have the year, the hits, the doubles, the triples, the home runs, etc. Okay, so that's the table we're going to use today. And we're only, actually, why is 1904 there? I guess they play. I'm only going to use recent games. I'm going to start around. I like to start at the earliest, 1947. Anybody know what happened that year? What's 1947, baseball fans? Huh? There's a more important event. That's when Jackie Robinson started playing. So before then, they separate. Oh, is that what you meant? They merged the. Well, it's when they started letting everybody play baseball, and not just some people. Okay. All right. So back to what people think is important. We're gonna go pick players, and right now, if you just go to what the leaderboards, what people are like, these people who are gonna get prizes. One of them is called the batting title. So that's whoever has the highest average. So there's that guy, very few people know, Altuve. I've never heard of him until this year, and he won the batting title. So that guy has the highest batting title. Is he the best player? Is he the one who should get the most money? Well, we'll see that maybe not. So there's also home runs and RBIs and stolen bases for some reason. Okay. So let's now start thinking about prediction in the context of all this. So what we want to do eventually is to predict runs. And then we're going to start with batting averages, and we're going to learn about regression today. We talked about it a little bit during the data exploration, summarizing. Today we're going to go into more depth. All right, so the question I'm going to ask you, so let's say we're picking, we get to pick players, and we have seen them on their first year, and now we get to pick them for the second year. So sophomore, and there's rookies. We're going to get to rookies in a second. So let's say I want you to tell me, what we want to do right now, just to keep it simple, is we want to predict the batting average of a certain player, of some players or a group of players. So let's ask the question, and we're going to think about now in terms of prediction. If I told you that I'm going to pick a random player, a sophomore, second year player, I'm going to pick it at random, and I'm going to hide him from you guys, and you don't know who it is, and I just ask you to guess their batting average. What do you do? What do you guess? What's your guess? What do you predict? I should start using predicting. What do you predict is their batting average? You want to get as close as possible to the right answer. What would you do? Just you have the data in front of you, so you can even say a number. Anybody want to yell out something? 270 what? What did you do? What did you say, 278, 9? It's the average of all the players. So when we look at this data, we can think of it, we can immediately see that and this is real data, by the way. You're not seeing any simulations of any kind today. It's all real. So the data, it's pretty nice. It looks pretty normal. That makes sense. The central limit theorem is kicking in, I think, here. This person is going up to bat. They're hitting the ball, and there's a lot of luck involved in what happens. You know, he might hit it really hard right at someone who catches it, and it's an out. He might hit it really soft, but it goes right to the right spot on the field, and it's a hit. So it's a sum of zeros and ones. It's like a random 0-1 thing, a Bernoulli trial binomial distribution. So it looks like that. Okay. Now this is across players, though, so that's a little bit different. So now we're looking at a series of players, and they also look normal. So that's a little different, because that's now nature somehow. Or unless they're all the same, and then all the differences are explained by random variability from sampling. That could be it. But if there is a player effect, which we think there is, and we'll see in a second that there is, it also seems to somehow be normal, and that could just be nature, how it is. When people are being created, they are assigned a batting average at random following a normal distribution. All right, so 280, 279, 278, that's the mean. If it's normal, that is the place where you have the most people, so it's the best guess. It gives you the best chance of winning. There's another property that the mean has, and it's that if you take the square of the difference between your prediction and what's the truth, the mean is going to be the number that minimizes that square on average. If you do it over and over and over again, the mean is going to minimize what's called the least squares, the sum of squares. All right, so 270 was a great, 280, 279, whatever somebody says, a great answer. It's the mean, and you'll do better than anybody else that picks something different. Okay, but now I'm going to change it, and I'm going to ask you for I'm going to tell you that the person that's behind door number 1, their rookie year, they hit 300. So now what's your guess? So last year they hit 300. Now we're going to predict. What do you predict for their next year, their sophomore year. Go ahead, what do you say? 250? Okay, so you're saying it was all luck. Okay, well that's a lot of regression. Okay, so you're getting to where we're going. Okay, so here's the plot now. So now I'm going to show you the data, and I'm going to let you revise your prediction. So you have, that was regression away from the mean, by the way. So way past the mean. So the mean is the mean is 280. We just said that. So here's the rookies and here's the sophomores. And what I'm asking you to do is predict for somebody who batted 300 their rookie season, what they're going to bat their sophomore season. And what we do, and we did this already when we did it before, is we take all the players that hit 300, and we look at that strip to create our prediction. And if we do that, we have a slightly different histogram. Right? So you see how it moved slightly to the right because there's correlation. There's a relationship between those two. There's some predictive power, and we can do the same thing again. Now for that group of batters that hit 300, we can then take the average of them, and that also looks normal. Okay, so so just to be clear on what I'm doing, this is actually 295 to 305. That's the little strip we use. So we have this little strip. We only look at them, and now it's, what's your guess now? It's like 290 something. 290 something, yeah, maybe 290. So somebody said regression to the mean. That's right. Not so much. You don't go past the mean. It's just a little bit less. Okay, so everybody see what we did? We took the strata, and we predicted just there. So that approach can be generalized, and you're going to see in the next lectures when we talk about machine learning and all this other stuff, the same rough idea remains. It's kind of a general idea behind machine learning and prediction. So here's how mathematically you're going to be seeing it in class and going forward. So what regression does is it says, if you want to make a prediction for an outcome y, in this case it's the sophomore's batting average, and you know something about them, you know that some x, in this case the rookie season average, you're going to take, and this is what this expression means, you have the expected value, the mean, average, of y, which will have a distribution, and now you have a new symbol. That little line means conditioned on or stratified by. So you stratify by x, condition on x is the official name we use, and we look at the distribution when x, the other variable, is whatever we are interested in. In this case I said 300. So we only look at the y's for the x's that have 300 that has a distribution, and the mean of that distribution is our prediction f of x. So if you, in machine learning, the entire field can be described as techniques for estimating f of x. Because as we move forward, we're going to see many situations where this little line idea doesn't work anymore. It gets more complicated, and then estimating f of x is hard. And it involves advanced and complex ideas. But the general idea is the same. We're trying to describe the conditional expectation of the variable we're predicting conditioned on some predictor. And the other thing we're going to do later is we're going to add more x's. Right? X, although in this formula, x can be multidimensional, and it's taken care of. Okay? So I hope, so when I think and I see that little strip, I think that's what my head pops into my head, that formula. That's what if you're going to be doing machine learning, you're going to do in prediction, you should start thinking like that. You want to predict, you take a little strip, you look at stuff in there, and then you do that. Okay, now, so here is that data turned into this little formula, kind of, right? So what we're going to do now is we're going to do that. We're going to make an observation about this data that makes this a special case that makes this pretty easy to do. So let me just say a little bit more so you start thinking about machine learning about this. If I use the actual number, 300, as opposed to a little strip, there's going to be very few players that have that number. It might just be one. In which case, now you're taking the average of 1, and that's going to be, in practice, it's going to be a terrible estimate of the real mean. There's a real mean there, that's fx. But now when we look at the data, if we try to estimate that f using the data, and we only have one x, it's going to be a terrible estimate. We're going to have one number to estimate one parameter, and it's no good. So a lot of machine learning involves trying to come up with, you come up with techniques to somehow estimate f of x in cases where you only have one x, but you can somehow learn about that x from others that are around it or some other trick like that. And you're going to see several examples of that. Today we're talking about regression, which is an example of that, where we're going to have a very nice form for fx. So that's what we're getting at now. But for now, what I'm going to do is I'm going to use a very simple technique, which is to stratify by having little bins. So I'm going to say 250 to 255, 255 to 260, etc. And then we get a picture like this. So you can see for every value of x, you have a distribution of y's, and the little line is the median, which is close to the mean. And when you look at that figure, you see something that's special about this data set. What is it? Is there something about the means? The little lines, do they follow some rough shape? How would you describe that? If you follow the little middles, the means. What does it look like? It's a line, right? It's close to a line. Here's the actual means, the little points. You see the little points? Those are the means at each strata, and you can see that it roughly follows a line. There's some variability that has to do with noise of the estimate, but it's roughly a line. Now, I'm plotting there another line. That's the identity line. And we're going to talk about that in a second. It's a line, but the slope is not 1. It's a little bit less than 1. It's like 41, I think. Okay, so it looks like a line, and it turns out that the simple regression like we're doing here, you assume that the data, that the most simple way to explain regression is that you assume the data is bivariate normal, that both, what does that mean? That means that both x and y are normal, and that at any strata, it's also normal. That's what bivariate normal means. So it doesn't matter what section you take, either on x or on y, the other variable also follows a normal distribution. So it's a series of normal distributions that if you have that property, then the formula for f of x, e of y given x is actually a line. And that is the regression line. That's what I'm putting up here. So when you have bivariate normal data, then that line, that f of x is, you can show it mathematically, that line there. See, that's a line y minus mu y. I'll say what that is in a second. Okay, so what is that? See that formula up there? Y minus mu y divided by, so let's explain what that means. So I want to predict y. I want to predict the sophomore batting average. And I am given the rookie season batting average was 300. So I say, okay, let's simplify this so I don't have to think about batting average and just think like a statistician. X, batting average minus the average of all the rookie batting averages divided by sigma x is going to be about 1 standard deviation, a little bit more maybe. So this person in their rookie season, they were about 1 standard deviation away from the mean. So now my question is, in standard units, tell me how much better should this person be in their sophomore year? So if he was 1 standard deviation better on their first year, how good is he going to be his second year? Is it going to be a standard deviation away again? Many people, that's the first instinct. They say, oh, that's how good they are. They're 1 standard deviation better. So the next time around, they'll also be 1 standard deviation way better. But if that were the case, if everybody just moved like that, what would the plot look like? If everybody that was 1 standard deviation away on one dimension would also be 1 standard deviation on another. Everybody that was 2, also 2. Everybody was 3, 3, -1, -1. What would the data look like? Yeah. It would be not on the identity line, but it would be on a line. Why is it not the identity line? They might have different means and standard deviations. But yes, they would be on a line. They would have perfect correlation. So twins' heights is close to that. So if you have a pair of twins and you know one twin is 1 standard deviation away from the mean, your guess for the second twin should be about 1. But if you have if a cloud like the one we saw, that's not the case. If you have something that's uncorrelated, like IQ and height, then the fact that I am 1 standard deviation tall doesn't mean I'm going to have an IQ that's 1 standard. That's because there's no correlation, so there's no predictive power. So that's what that R does. Because the data is not on a straight line, that means that then the predictions what was said earlier, must regress towards the mean a little bit. That's what that R is. So that R is a number between -1 and 1. There's a formula for how you compute it. If you look at that formula just for a little bit, you're going to see that if those two numbers, if the distance from the mean is moving together, then those numbers are going to be going to be positive together and negative together. So they multiply up. They're close to 1, and that average of those numbers is close to 1. If they're in opposite directions, then the signs are negative, and that number is going to be close to -1. If they have no relationship, it cancels out. Sometimes it's plus, sometimes it's minus, cancels out, R is 0. So for twin heights, it's about 9.9, I think. For IQ and height, if you don't include children, it's 0. If you include children, it's a very high correlation because they're little and not that smart. And height of father and son is about 0.5, and in batting average, it's 0.41, rookie and sophomore season. So if we're going to predict someone's batting average, all we have to do now is stick that 0.41 into that formula, and we're done. We don't have to make the straight or none of that. We don't have to do any of that. Just a formula. All you need are 5 numbers. The mean, average of the rookies, the standard deviation, the average of the rookies, same for the sophomores, that's 4, and then the correlation, 5 numbers, you have that line, and you're done. So the slope of this line is 0.41, not 1, 0.41. Twins would be on that. These guys are down here. Okay? Any questions? That's regression. That's what regression is. You're basically saying you're predicting the number of standard deviations away for one variable given another when you know the correlation and you know they're bivariate normal. Okay, one other little detail. That R, the correlation, that number, more generally the line that's formed here, the line that eventually ends up being given by that formula up there, it has 2 parameters, the slope and the intercept. You can also get them by fitting what is called least squares to the data. So what you do is you say, sorry to go back. You come back, all the way here. You go to that data set and you say, what's the line that fits those points the best? Meaning, I draw a line and then I take the residuals, the distance between y and the line, and I find the line that minimizes the least squares. That gives me the same answer. It also gives me the regression line. Least squares gives me the regression line. Okay. Sorry, let's do this. All right, so one other tiny important, well, not so, a very important point to make here also is that the standard deviation of our new strata goes down. That's good. That's when we're thinking about prediction. what we're saying is we're making a prediction. So here's all the sophomore averages. Right? So up here is 280 in that mean. And then it has a big spread of different players. Now, when I look at just the 300 batters, the mean goes up a little bit because they're better players, and the standard deviation shrinks. Now we have a better idea of what they're going to be batting. And how much does it shrink has to do with the correlation too. If the correlation is 1, there's no variance. I know exactly what it is. There's going to be no variance. It's on a line. If I know X, I know Y, no variance. And if there's no correlation, I'm not gaining anything. If there's no correlation, then I get the same variance again and don't learn anything. But here I learned something. I said move a little bit up, and also now you're going to be a little bit more sure of yourself when you predict. So the more correlation there is, the higher that goes and the variance shrinks. Okay, so now let's talk about the regression fallacy really quickly. Remember when we had the Madden game and we talked about the curse of Madden? So the curse of Madden, Madden is this famous coach that now is, I don't know if what his involvement is, but there's a football game for Xbox that has his name on it, and I guess he picks the best player of the year, and that player gets to be on the cover of this game. And it turns out that people notice that player, when he's on the cover, he doesn't do that well the next year. So they call it the curse of Madden. In baseball, they call it the sophomore slump. When they look at the best rookie, they look at him next year and he doesn't do that well. They're like, oh, he must feel all this pressure from being the best, and now he's doing terrible. So here are some examples. These are the best batting averages of a rookie in the history of baseball, or at least since 1947. John Allrood, anybody know who that is? I know who he is. He batted 363. That's very high his first year, very high. Wade Boggs. You guys know who Wade Boggs is? He's very famous too. He played in Boston for a while. Had a big mustache. I don't know if anybody know who this guy is. I don't know. His first name's Noel Cash. Well, anyways, I don't know what his first name is, but his last name is Cash. And he batted 361. That must have been in the 50s or 60s because I have no clue who that is. Alex Rodriguez, you know who that is, I hope. A-Rod. He's a bad guy. Everybody hates him. He hit it 350. Okay, and then who's this? Madlock, somebody. I don't know who that is either, but he batted 354 his first year. Oh, yeah, I know who that guy is from the Pirates, the 70s. Okay, Tony Gwynn, great player. He just passed away, sadly. 351. Okay, anyways, so, Ichiro, Mauer, a lot of famous people up there. So look at the second year. They all did worse. Oh, my, the pressure. Poor guys. They can't take it. There's no exception to that rule. They all did worse, especially poor Mr. Cash, who now we don't know who he is. So is it pressure or what is it? Why is that not? Why is there a much lower average? It's because the correlation between year 1 and year 2 is not 1. That's what it is. If it's not 1, that has to happen. It has to be the better. The people who have a lot of standard deviations away get shrunken down towards the mean. And on the other side of the coin is the, I guess I don't know what to call this fallacy, but all the people who did really badly, now they're all relaxed, so they can just take their time and have fun, and now look how much better they do the second year. Same thing, right? Because the correlation is not 1, the lower part has to come up. Regression to the mean. Now in the case of that original term, or regression to the mean, came from heights. So when Galton, I think, one of those famous statisticians / geneticists, was looking at Pearson or Galton, can't remember, was looking at the heights of sons and fathers, He noticed that. He noticed that the tall fathers had sons that were slightly shorter. So in that case, the explanation is that the tall men don't exclusively marry tall women. They kind of mix up. They do tend to a little bit, but not too much. So the son is half mom, half dad when it comes to height. So they regress to the mean. Right, so there's an explanation. There's a physical explanation for why that happens. Now here, anybody want to take a, there's no right answer, but anybody want to give an opinion about why there's regression to the mean in baseball averages? And it's actually the reason I think it happens is the reason it happens the most of the time with regression to the mean. Any ideas? Want to share? Is it the pressure? Does anybody believe that part, that story? Could be. Yeah. So I think that's an overinterpretation that people start like, oh, this guy's good. Let me pitch him a different way. But that's possible. There's some of that. They're like, this guy, just go ahead and hit it, you loser. Okay, so I think that those are all possible explanations, but I think the main one is that luck. Your luck doesn't correlate with next year. There's some luck involved. So the best batter probably is good, but part of the reason he won to be the number one, there was some luck involved, and they don't get that luck again. I mean, it's not that it averages out, it's just that chances are they won't be as lucky again. Right, so what you're seeing are, towards the top part, the errors are positive. The next time around, the chances of you getting a positive error again isn't likely. So you have your true talent, so someone like, let me look at the other one. So someone like Wade Boggs, yeah, he's great. He's a great hitter. He's probably like a 340 hitter and got lucky, and it went to 360. Next year, he got a little unlucky, so it went to 325. And across his career, he probably was around 330, 340. Okay, so that's what I think happens here. In a lot of instances, that's the explanation. So you also see you see regression to the regression fallacy in the media a lot. Not a lot, but you see it often. One of my favorites is that with exams, the same thing is shown. Somebody wrote a paper about how the best scorers don't do that well the second time because they feel the pressure. The same story, and again, the correlation between your test scores in exam 1 and exam 2 is not 1. So there has to be regression to the mean. The top people, many of them have to come down. Otherwise, the correlation would be 1. Okay? All right, so now let's do some Moneyball. So we want to pick players. And players, we have all this data for them. So one very simple thing we're going to try first is to use the aggregate of the teams to see what statistics predict runs. So the problem, we can't use the player's runs to predict the player's runs. So a player also has runs as a statistic, and it's how many times the player scores a run. But that's not just him. That has to do with who bats after him. So it's not a good predictor at all. So here's a plot of batting average, runs against batting average for teams across several years. And not surprisingly, it correlates. Teams that hit a lot hits get a lot of runs. So one thing we can do is try to pick players that have high batting averages. But that's going to cost you. Okay? So here's a plot of lifetime batting averages against lifetime earnings in millions. I wonder who that is up there. Anybody know who it is? Who? No, Barry Bonds. It's A-Rod. It's A-Rod. A-Rod's the big money maker. Okay, so you can see it's going to cost you. You want to pick 9 players that hit 320? That's, you're going to pay that much. So that's a strategy, but that's going to cost you. How about home runs? Those are expensive as well. There's A-Rod, 600 home. So these are the total number of home runs and the total salary earnings. Big, that's an even bigger correlation. Costs you a lot of money to get home run hitters. Okay, so now let's look at other stuff. See what we can find out. Okay, so now we have 6 things up there. One is the average. We already saw that. They're all plotted against runs versus stuff. The first one is singles. So now I've taken hits and I've split them into doubles, triples, home runs, and singles. Look at that. Singles. Look at how much they predict runs. You would think that it's a good thing. When you're in Little League, the coach is like, don't hit a home run, just hit a single. Well, he was wrong. I was right in swinging for the fences. That's true, I was. So you can see singles are not very predictive. So getting to first base with a single is not very predictive for us. Now, it's a good thing to get on first, of course, but why do you think it's not predictive of runs? Or it's just a little bit predictive of runs? Given that it gives the team a chance to score you. Any thoughts on that? So, any thoughts? Yeah? That's one reason, but we're going to get to some balls in a second. But I think it's because singles are just luck. Okay, so singles, so the reason a team that has a lot of home runs is just a better offensive team. Forget about the home runs. They're just going to be better. A team that has a lot of singles one year, I think that might just be that they got lucky. If you think of baseball, this is now, you need to watch to see this, there's a lot of things that will get you to first base that aren't very impressive at all. Infield singles, bloop singles, ground balls that go through they're just in general not impressive. Now, doubles does predict runs. So doubles when you get to second. To get to second, you have to hit the ball hard. Triples, they're not predictive, and I think that's because there's very, very few triples. I forgot to mention, look at the x-axis. You see that I have some weird numbers there? What I'm reporting is the hits per plate, singles per plate appearance. So that means 16% means that team, 16% of the time, got singles. By the way, another thing I forgot, a team that has a lot of singles then has less of the other ones, less doubles, triples, and home runs. All right, home runs, very predictive. Oh, it's the best one. And then we have, this is the big surprise. Not anymore, but it used to be. Base on balls predicts more than singles. So all these titles we saw, these trophies and stuff they give away, nobody gets a trophy for getting on base on balls. But it's important. And that was what these Sabermetrics people were saying. Look at base on balls too. It's just as good as getting on in other ways. Use that. And the reason that I think the A's did well is because they're not expensive. So when you want to buy, you can buy a player that gets a lot of base on balls for a low price. For a low price. And there was people like the names, I won't tell you the names, but there were several people on their team that were good at this. And nobody wanted them. All right, so base on balls are not as expensive. So we're going to use that. You can use that to improve our predictions. Okay, so we're going to do one last thing. We're going to actually try to predict some runs, and then look at a couple of players and see which one produces more runs based on this little model. So here's now what we want to do now is we want to predict the runs based on these other things, and we're going to fit a linear model. So now it's getting a little bit more complicated because no longer do we have this scatter plot that we can say, oh, it looks normal, so there has to be a regression line. Now what we're saying is we're building a model. This is more of a prediction model based on linear regression that says that the expected number of runs is a sum of some linear combination that says, okay, you have these many hits, I'm only using doubles, home runs, and base on balls. But I could use other things. I could use hits or average. So I'm going to say that is the function. That there's some function that depends on doubles, home runs, and base on balls that predicts the expected value of the runs. Okay? So that's a type of model that you use when you do prediction. There's going to be much better ones you're going to learn about next week. Okay, that's one. That's a big assumption because it assumes things add up, and it might not be that way. They add, and there's just a line. There's no curves or anything. And then we can add a further assumption. It's to say that the data itself is that function plus some variability, some random error that has mean 0 and some fixed variance. That's also another assumption. And if we write this down, we can actually get numbers for the betas by using least squares. So we find the beta 1, beta 0, beta 2, beta 3 that minimize the, I have it here. We find the betas that minimize that thing. And that's something on the computer is a piece of cake, and it's super fast. Using calculus, you solve this really fast. All right, so that gives us actual numbers that we can stick in and start making predictions. Okay, so now let's do it. So we're going to fit it for before 2012 because we want to pick players for 2012, and we're going to do that. Now, before we continue, there's something you should be aware of when you're on your homework because this might confuse your analyses if you don't realize it. So I might as well tell you now. This is the runs, the runs for every team against year, starting in 1960. Okay, so anybody know what happened in 1995-ish? That's right, steroids. Juicing. People started using steroids, and you can see it there. And you can see when they started being careful about the bans as well. This is the glory days of baseball. Barry Bonds, Mark McGwire, Sammy Sosa hitting home runs all over the place. Alex Rodriguez. All right, so that's something you should know. But there's other trends there, but that's the big one. And there's also a strike. You see the strike? I only include data with 162 games. There was a strike that year. They didn't play all the games. Okay, so here's what if I fit these models before and after the yeah, I don't know if you want to see this, but I fit that model and then I compute the sum of squared errors. So I take the residuals and I square them to see how well I did. I fit it before 2001 and then fit it after 2002. So Vernon is going to talk about this in detail on Tuesday, but it's something you want to be aware of, that we fit the model on one date and then we test it on another to be realistic. So these are three models, one that has only average and home runs, and average home runs and base on balls. And you can see that adding these other information improves your prediction of runs. That's all you need to see here. Okay, so now let's okay, we have a little bit of time. So now let's talk about picking players. All right, so some slight complications of doing this. When I fit that model, and then I try it on another year. I'm using the runs, I'm using the hits and the home runs and doubles for that year. So those have to be related to runs. If you got lucky and you got a lot of home runs, that's going to give you more runs by chance. And that makes it so that if you were going to predict without getting the data for that 1 year, if you're starting the season, you're not going to do as well because you have to go with data that you don't have yet. So So when we're doing these things, when we're trying to predict the best team that we're going to choose, we're not going to be able to use the data of that year. We have to just predict with everything that came before. So that's something important to keep in mind for the homework. So you have to test these things with the numbers of for example, the year right before. So because we're doing this, there's something important that you want to realize is that, and this is also comes up in other machine learning challenges. When we're predicting runs with batting average, we're using a variable that's also random, or it can be thought of random. So batting average, here's Derek Jeter. There's his batting average through the years. You see how much that moves around? It's moving around. There's a lot of luck involved in hitting. So, some years he was luckier than others, or some will say, oh, that year he was in the zone. Or it could just be luck. But still, he's good all over. I mean, he's always oscillating around 320. So it's clear he's clearly a very, very good hitter. But I guess what I wanted to show you is what happens when I take, okay, so here's what this plot is. So I take all the years before he came to the league, and I build a model that says runs are a linear function of average with teams, just with teams, not with players. It would have been better if I had used players. And then I say, okay, now if I had it, so now I'm going to stick in the numbers for Jeter. After I fit the model, I now have numbers. I can stick numbers for Jeter, and now I get runs per game. I change it to per game. So if you think that model is right, that with average you predict runs, then and you do it for Jeter, you can see a team that would be a bunch of Jeters, just 9 Jeters, would score about 6 runs per game, and it kind of oscillates all over the place. Right? It oscillates the same way the other one does because average is the only input. Okay, so if I instead use our little model that had doubles, home runs, and bases on balls, that's what the orange line is. So what that tells us is if you focus on those, then he's not a player that hit that many doubles. Well, he did, but not too many home runs. So it's not as high. It's still pretty good. 5 runs per game is good. But the more important thing to notice, and I think it's more for machine learning purposes, is that there's less variability. You see how it varies less than the other one? So if you focus on some kind of average of home runs and bases on balls and doubles, there's less luck involved, I think. So then that thing varies less. So it's a more stable predictor of runs. Okay, and then the last picture is the same for David Ortiz, who would, if you use the average model, he would score only, his team would only score 6, but if you use the other one that includes doubles, home runs, now we're talking about a team that scores 8 runs a game, and that would win most games. Okay, so I just want to show you how you can get very different predictions using different inputs based on the numbers. So for the homework, you want to take this into account. You want to pick a model that predicts runs and using stable inputs, and hopefully you'll be able to construct a team that is cheap and also produces lots of runs. Okay, so that's where I'm going to stop, and I'll take any questions you may have. Any questions? Yeah. Sure, yes. Everything depends on the pitcher. Based on balls on particular. So these are now questions that I want you guys to start thinking like data scientists and think about that. So yes, it does. Now you say, well, that's going to be biased, and then if you some players got better, faced worse pitchers than others. But is that something that you really think would be a problem here? So it might be, but you can think of the pictures that you get as a random sample. If you believe it's something like a random sample, then some players won't be favored more than others. See, so it is, if you really want to do this very, very carefully, you would probably take who's pitching into account and correct for that some way. Right? So if you're in a league that has better pitchers somehow, yes, that's something to keep in mind. But again, start thinking like a statistician, like a data scientist. Well, how much of an effect can that have when you have so many people pitching at you, and that if there are good ones, there's also going to be bad ones, and hopefully the whole thing averages out. Right? So you want to be thinking like that. So that's a great question, and you want to think about answering it to your satisfaction. There's not one right answer here. Another question? Yeah.
So what is the story you can tell that would explain that singles are not as indicative of runs as walks?
So the story, I think it's, as walks. Yeah. So in this case, there's a little bit of, so the one problem with the plots I showed you want to make better ones, is that I'm using the same year. If I'm using the same year, singles and home runs are going to be probably anti-correlated. So you have a lot of people in the single, they have a lot of singles that don't have a lot of home runs, so that might affect it. Well, base on balls and home runs are probably correlated. People who, you can check that. So home run hitters tend to be walked more because the pitchers are afraid to let them hit. So really that plot, there might be some confounding there. And it's not really, it could just be that's not based on balls, it's predictive. It's the fact that people with a lot of home runs get based on some balls. And so there are ways to get around that, and you can start trying to explore that. But yeah, great question, because it reminded me that plot I showed was just didn't take into account confounding. You could stratify, you can make that plot for home run categories and see if the correlation still stays. You see what I mean by that? Like if you take people who hit less than 10, people who hit 10 and 20, 20 and 30 home runs, 30 and 40, what is the correlation between walks and runs within those strata? Yeah. Yeah? I don't know if it's too subjective, but would you consider leaving out the steroid error from your regression if you were characteristically high? You know what? No. Why not? Because yes, that's another good question. You want to think about that too, because what are we trying to? The fact that they use steroids doesn't matter for these purposes, because the home runs happened, and if they're predictive of runs in some way, it happened, right? It has nothing to do with if it's a steroid user or not. See what I mean? So the information I think is still useful, because now, okay. So the question then would be if you pick a player that was, if you're now at the player level, then it might matter a lot, because if you pick a player that you're basing your choice on that player for what he did in the steroid data, and now all of a sudden you pick him and the steroid era is over, he might drop way down. So in those cases, you might want to take it into account. But in 2000, the homer's going to be for 2002, so they're still juicing, so you can keep them. So I think it wasn't until later that they started getting caught, right? So yeah, you can pick Palmeiro. Palmeiro is a player who had a big drop. It was very obvious when they accused him. Then all of a sudden it was like. Any other questions? Yeah. So on Tuesday, Verena, you're going to go that deep into overfitting and all that. So that's part of what you're going to learn in the class. The short answer is there's a procedure called cross-validation, where you test your procedure on a data set that you did not use to fit the model. And that protects you from that problem. It is a huge problem in machine learning. That if you fit big enough models will predict the data perfectly. But we have many solutions for avoiding that. And again, the short answer is cross-validation is what you want to do. And it's easy to do here with this data set. It's so big, you can pretend, you can keep data out, keep teams out. You can do all kinds of stuff to test yourself. Yeah.
When you were looking at predicting sophomore averages on rookie average, you were not considering number of at-bats, right? Were you assuming there's a certain minimum number?
Yeah, there's 500. I only showed, I forgot to mention this, I only showed what are called eligible batters, 502 or more at-bats in that plot. So some of those people might be year 1 and 4 if they got hurt during their second year. So what that plot really is the first 2 seasons that the batter hit 502 or more, which for most of them is going to be rookie season and second year, but not all. Yeah, 502 is a minimum required to win the batting title. Yeah. Mm-hmm. Yeah, absolutely. Yeah, so what she's saying is that you can't really extrapolate from teams to players necessarily. Yeah, it's true, and it's a limitation of this homework. If you want to get into the player level stuff, it gets really complicated, and people do it. There's something called the most famous statistic is called the wins above replacement, where they really try. I don't know how well they do. They really try to answer that question at the player level, and they try to figure out how many wins how many more wins that you win with that player compared to if you had like a minor leaguer. And that, I think the way they calculate it, I'm not completely sure, but I think they calculate that with single individual level data. I'm not completely sure though, but it is something to think about. Yeah, definitely something to think about because it really helps you see everything that's involved here. The solution to the homework and the stuff I presented here is not optimal. It's not what teams do. It's just trying to get you to see. It's to get you to ask questions like that. If you're asking yourself questions like that, it means you got what we're talking about here. Yeah, back there. The percentage, we can see it from here, I think. Oh, I passed it. Too fast. There. Okay, let's see. All right, so we have 16% of plate appearances are singles, 4% are doubles, less than 1% are triples. You see the number I'm looking at here? About 2% are home runs, 10% are walks, and the rest are outs. 60% roughly of the plate appearances are out. So in baseball, the best player fails more than half the time. It's like a little joke that people say. Like a great player fails 70% of the time. No, 60% of the time. So 60, about between 70 and 60% of the time, a player gets an out. There's some rare exceptions that, like Barry Bonds, Babe Ruth, they were amazing at that not making outs, but in general, that's the case. And then the rest is split up this way. There's other things, if you're interested in, there's errors, there's sacrifice. Better not to think of those. Okay? All right.